Well, our next topic here in probability concepts is dependent versus independent events. Let's see, it says here, knowing the outcome of one tells you something about the probability of the other. Well, that's right, dependent events. So if I'm looking at the returns on Exxon and British Petroleum, BP, well, they tend to move together. They're both multinational oil companies. So if there's a shock in the oil market or something, they may move in the same direction. So knowing the returns on Exxon maybe gives us a little clue about what the returns for that period would be for British Petroleum. So those are dependent events. Now, in terms of our probability symbols, we've got the probability of A given that B happens is not equal to the unconditional probability of A. So it has some information for us. That's all we're saying there. Now for independent events, knowing the outcome of one tells you nothing about the other, about whether it's going to be above its mean, below its mean, positive, negative, or whatever. And so with our symbols here, we've got the probability of A, given that B happened, is still just the unconditional probability of A. Next up here is our total probability rule. Now, we're looking at our conditional probabilities here, and in our simple example here, we've just got two possible second events here, B. We've got B and B with that C by it, the complement of B, which means basically not B. So we're saying, well, if you've got the probability of A given that B happens, times the probability of B happening, and we add that to the probability of A happening given that B didn't happen, times the probability B doesn't happen. If we add all that up, we get the unconditional probability of A. And the intuition here is just, well, that's the only ways you can get A. There's only two states of the world here. B happens and B doesn't happen. So if we figure out the probability of A with B happening and the probability of A with B not happening and add it together, we've got the probability of A. And we can generalize that. So as long as we've got here, instead of B and not B, now we've got S1, S2 through however many finite different outcomes there are for this S, or events there are for S. And so when we add all those together, we get the unconditional probability of A. And I guess the conditions here, well, these probabilities of S, that's again all the possible outcomes. So that's 100%. That sum of those probabilities equals 1. And so they cover everything. And the other thing is they're mutually exclusive, right? The S1 and S2, no overlap. It's either or. Just as we started out with B and not B. Mutually exclusive and cover 100% of the possible outcomes. So here's an example for our unconditional probability. We're starting out given the information that the probability of an interest rate increase is 40%, 0.4. The probability of no interest rate increase, the complement of I, is 1 minus that, 60%. And then we're given a conditional probability here. Probability of a recession given an increase in interest rates is 70%. And the probability of a recession given no increase in interest rates is 10%. Well, we've got all we need to do. It's like our B and not B. Here we have rate increase or no rate increase. And so if the question is, what's the unconditional probability of recession, we're just going to multiply these conditional probabilities times the probability that that second one will occur or not occur, adding those together, and we get 34%. So that's our unconditional. If we don't know anything about whether there's an rate increase or not, our expectation is that there's a 34% probability of a recession, the unconditional probability of recession. Next up, expected value. This is just a weighted average. what are the weights? The weights are our probabilities. Well, they sum up to 100%, so it works for a weighted average. And here we've got 4 different outcomes for earnings per share for Ron's stores. And we've got the probability of each one. So, statistically speaking, our expectation of earnings per share is that weighted average, which comes out here to be 1.28 pounds. So, you can see 1.28, it's nowhere here. And yet, the idea is that's our expectation because, just as before, given these outcomes, our expected error using this expectation is smaller than the expected error of using any other expected value. So that's the statistical property we like about this weighted average of the earnings per share outcomes. Next up for us here is calculating the variance from a probability model. So if we have a probability model, these percentage probabilities for, in this case, 4 different outcomes. In order to calculate the variance, what we're going to do is we're going to take the deviations from the mean. So we're subtracting the mean off of each of our 4 possible outcomes. And then we're squaring those differences. And then we just take the weighted average of those, with the weights being the probabilities. So we calculate our variance here as 0.0736. Well, the units of variance are conceptually more difficult to get a grip on than standard deviation. But you can see if we take the square root of this, we get right back to pounds. So our standard deviation, square root, 0.0736, is 0.2713 pounds. So that's our standard deviation of the distribution based on this probability model and those squared deviations from the mean. So now we'll take a look at using conditional expectations. So we start out with the information that the probability of a tariff is 40%, probability of no tariff is 60%. And so maybe we're looking at steel companies or something and whether a tariff will be imposed on the importation of foreign steel. And so we're given further information here. The expected return on this stock we're looking at, if there's a tariff, is 15%. If they get some protection from foreign competition, they'll have higher returns. And the expected return, if there's no tariff, is lower. It's just 5%. Well, here we're just using a simple weighted average, probability weighted average. Our expected return, using these conditional expectations, is 9%. 40% chance of the 15% return, 60% chance of the 5% return, and that's where we get our expected return. But again, see, that's without knowing whether there's a tariff or not. That's our expectation. Once we know if there's a tariff or not, we can refine our expectations to either 15% or 5%. Now here's a handy tool, an investment tree. So let's see what we're looking at here. We're starting out and we're taking a look at GDP growth. We've got 2 possible outcomes here. GDP growth greater than 3% and GDP growth not greater than 3%. And our probabilities are 60% and 40%. But the tree part is now, given each of these first outcomes, we're going to further look at 2 possible outcomes from there. So on our top branches of the tree here, we said, well, if GDP growth is greater than 3%, we expect earnings per share are going to be pretty good. There's a 30% probability they'll be $1.80, and 70% probability they'll be $1.70. And if GDP growth is lower than 3%, well, earnings aren't going to be as good. Our model tells us there's a 60% probability earnings per share will be $1.30 and 40% probability that they'll be just $1. So that's our investment tree, and we're going to use this to look at conditional and unconditional expectations. So we can get our probabilities. We get the 18% just by multiplying out this way. 0.6 times 0.3, that gives us an 18% probability of that earnings per share. And you can see, what will our next number be here? Well, 0.6 times 0.7, we're going to fill in 0.42. We're going to get 42% probability there. And as we move down the tree, 40% times 60% is going to be 24%, and 40% times 40% is going to be 16%. So if we fill all those in, and you can see if we add all these up, that's 100%. So that covers all our possible outcomes. So now we can start talking about expected earnings per share because we've got probabilities for 4 different outcomes. We can use the probability weighted average for that. And the other thing we want to look at here is our conditional expectations. Well, what's our expectation of earnings per share given that growth is greater than 3%? Well, then we'll just be using 30% times $1.80 and 70% times $1.70. So we can get our conditional expectations looking out from here, or our unconditional expectation looking at all 4 of the outcomes. So our expected earnings per share, that probability weighted average of earnings per of those 4 earnings per share numbers, is $1.51. And again, $1.51 is never going to occur, but it's our best guess given this information and these probabilities. Now we want to take a look at how 2 variables move in relation to each other. We talked about independent versus dependent relationship. Well, if we've got some positive covariance or negative covariance, then the movements of one does tell us something about the movement of the other. And if both variables tend to be above their means in the same periods and below their means in the same periods, then we've got a positive covariance, means they tend to move together. So if we were talking about Exxon and British Petroleum, well, since a lot of the factors that drive the values of their stocks and expectations about their future earnings are the same, they're going to tend to move together. We would expect to see positive covariance. However, if we looked at an airline versus an oil company, well, airlines, their expenses get pressured when fuel prices are up, and their returns are not as good if we get a spike in fuel prices. And yet a spike in fuel prices is good for an oil company, or typically is good for an oil company. So they may have negative covariance. In that case, one variable tends to be above its mean when the other is below its mean. Good oil returns, relatively poor airline returns. And the covariance of any variable with itself is simply its variance. So now we'll look at a probability model, and we want to get the covariance. Well, with the variance, we squared the deviations from the mean. Now we're going to take the deviations from the mean for each of them and multiply them together. So if one's above its mean, the other's below its mean, got a positive times a negative, we'll get a negative covariance. If they both tend to be above their means in the same period, both positive, and below their means in the same period, both negatives, multiplying them together will give us positive covariance. So let's crunch some numbers here. First, we're going to calculate our expected return for each stock. We just add them all up and divide by 3. Nope, can't do that. We've got to take the weighted average using those probabilities. So there's our weighted average of those 3 possible outcomes for stock A, and our weighted average of 3 possible outcomes for stock B. So again, here's our probabilities, and here's our set of 3 outcomes for each, stock A and stock B. So now we've got that. So now we're going to take the deviations from the mean, just as we did with variance, but again, if it was covariance with itself, we'd be looking down here and squaring all these deviations. But for covariance, going to multiply them together, and again, it's going to be probability weighted. So that's what we've got in this right-hand column. We've got probability times this deviation from the mean times this deviation from the mean, and we get 0.00336. And for a normal economy, there's our product of the probabilities and the deviations from the mean. And in a slow economy, we get that. So now what are we going to do? Well, we need to just add those all together, sum them up. And what do we get? We get a covariance of 0.00580. So here's what we've done, plus this equals that. Okay. Now we don't know, we can't say too much about that covariance because we're not really sure about the units of it here. It's squared percentage deviations from the mean or deviations from the mean in percent terms. The only thing we can really say at this point is it's positive. They tend to move together. Well, is that a strong tendency to move together? Weak? We know it's not exactly zero. That's about all we know. It's positive and it's not exactly zero. Okay. Now we can also calculate covariance from sample data. And so this is more like equal weighted, right? We've got n observations here and they're all kind of equally likely. But if we're using sample data, we're going to calculate the sample covariance. Our divisor isn't n. Okay? If it were n, we'd be talking about the average product of the standard of the deviations from the mean, right? Our cross product there. Well, we use n minus 1, and that's really just a statistical thing. That does give us an unbiased estimator of the true covariance, so that's why we do it. Let's look at a calculation. Now this is kind of simplified here. We've only got 3 historical returns. We've got 3 for A and 3 for B. So again, we find the means, then we take the deviations from the means, and we multiply them together. So we've got 3 terms, the products of the deviations from the mean for asset A and asset B. And then we're going to divide those by n minus 1, and we get 77. Now, I think I'll mention here that we get 77 because we've put in the percentages as whole numbers. That is, we put in 18%, which is really 0.18. We put that in as 18, so we get this as a whole number. What we're looking at here is had we put it in decimal form, we would have gotten this. And you can think about that the units returns are in percent. Well, 1% is 0.1, 0.01. And if we square that, we get 0.0001. And if we do 77 of those, that's what we get, 0.0077. So that's the relation between those two, just so that doesn't confuse you at some point. Correlation, standard measure of the linear relationship between 2 variables. Well, you remember I was saying that covariance, we knew it was positive. We weren't sure how strong the relationship was because what units we were in wasn't all that clear. Well, that's what correlation does for us, is it standardizes covariance. And so correlation is bounded by +1 and -1. And so we can look and see, and then we can go, oh, that looks like a strong correlation. That's getting up there around 0.8, positive 0.8. Or it's negative 0.1. Gee, that's negative, but it's not very strong. Now our notation here, this R is our sample correlation coefficient, and this Greek letter rho is our population correlation coefficient, just like we used mu for the true mean, Greek letter mu. So our Greek letters are the true parameter values, and our estimated values, our sample values, are regular letters. So let's just do a quick calculation here. What's the correlation returns between stock A and B, given, here's our variance of A, our variance of B, and our covariance? Well, we just have to use this formula. We're going to divide the covariance by the product of the standard deviations. So first off, we get standard deviation A and standard deviation B right here, and then take our covariance and divide it by both of those, and we see that now it becomes pretty obvious we've got a pretty strong positive correlation between these returns on stock A and the returns on stock B. Remember, it's bounded up from above by +1, and we're at 0.9842. And another good rule of thumb, if you're doing a problem and calculate your correlation coefficient, and it's bigger than 1 or less than -1, you might want to try it again. Here's an example of some scatter plots. Now, we'll use these at some point when we get to looking at the relation between the returns on a stock and the returns on the overall market, estimating its beta or market risk. So we're introducing this idea of a scatter plot here. So we've got two variables, and so each dot here, this is one of the outcomes, right, in our sample, and this outcome has this if this is our y variable and this is our x variable, doesn't really matter which is which. We'll see the same kind of relationship. So if our y variable had that value and x variable had this value. So that's the idea of the dots on the scatter plot. They're showing us the values for two different variables. So if we were looking at returns, we'd have the returns on one stock or one investment on one axis, returns on the other stock on the other axis. So now we want to take a look at, well, what does a scatter plot tell us? Well, just in examining it, sometimes it's obvious what the relationship, if any, is. Now, we see this first one where it says no relationship here, and there's really no pattern. And that would go back to our low correlation, right, or independence, knowing the outcome of one, knowing in, maybe this was the 13th period right here, knowing in the 13th period that our x variable was 4, well, does that tell us anything about our y variable? Well, not so much. That's the no relationship case. The second panel here shows us a linear relationship, and of course it's pretty extreme the way we've seen it. We say, well, the relationship between those two variables looks like that. Well, they clearly have a fairly strong relationship, and it turns out that when our y variable is high, our x variable is low. We've got a negative slope here, and that indicates a negative correlation between the two. But we also may have a relationship between two variables that is not inconsequential, but it's not linear. And that's what our third panel illustrates here, is there is a relationship between these variables, but it doesn't really fit a line here, does it? No. This is more of a sine wave, a curve relationship. So that's how we're going to look at and view scatter plots. And mostly we'll be dealing with linear relationships. And not only saying, well, yes, it's a linear relationship, but hey, what does the slope of that relationship look like? Is it steeply negative, steeply positive? Now, the thing about correlation is it doesn't show any causation. correlation does not imply causation. Even with that one where they were on the same line, well, it could be that one is causing the other. But the direction of that causation is certainly not clear. If we switch the x and y, we'd still get a linear relationship. So we can't say x is causing y any more than we could say y is causing x, just because there's a strong linear relationship. And that's what correlation is measuring, is that linear relationship. Variables with strong nonlinear relationships may have a correlation of 0 because, well, there's strong correlation maybe, but it's not a linear correlation, so correlation is going to be at or near 0. But it also may be that there's no causation at all. And one reason that might be is it just may result from chance. The other way that might come about is both variables are related to a third variable. So maybe we're looking at two variables and go, look at over time. Okay? Look at how tightly these are related in a linear fashion. But it might be that over that period of time there was inflation, and that both of our variables, if we're measuring them in nominal terms, they're both affected by inflation. So look, they both went up at approximately 2.5% a year over this 10-year period. So they may both be related to a third, or it may be just a chance relationship and no causation at all. So be careful when interpreting correlation.